Today we're going to be looking at the Laplace transform and a few examples. We will also be briefly looking at the applications of the Laplace transform for differential equations and solving improper integrals. However, the first application for solving differential equations, that won't be tested. However, if you do use this method in a test, I will give you the marks for that. Okay, but you won't be expected to know that for tests. However, the second application for solving improper integrals, that can and will be tested. Okay, so what is the Laplace transform? Okay, the Laplace transform is an integral transform that converts a function of time into a new function of frequency. Okay, so we have some function of time. Using this transformation, we convert it to a new function of frequency. Okay, this is used a lot in science, and specifically for you guys, engineering, specifically the mechanical and electrical engineering. Mechanical and electrical engineering. Okay, we won't be looking too much at the other use cases, but for mechanical and electrical engineering, we'll have a look at some more specific examples for those cases. Okay, so the two applications, like I mentioned. Okay, so number one, solving differential equations. Okay, so the Laplace transform allows us to convert a differential equation okay, into an algebraic equation. Okay, that is much easier to solve. Again, you won't be directly tested on this application. However, if you do use it for the test and exams, I will give you the marks for that. Yeah, but you won't be expected to know that. Okay, and number two, solving improper integrals. Okay, so we've looked at a few improper integrals with infinite bounds, and we solved them writing the bounds as some variable, let's say t, and then at the end of the integration, we then took the limit as t goes to infinity, for example. Now, a lot of those problems that we looked at were fairly easy to solve. However, some of them are much more complicated. And so we use the comparison theorem to check that they are either convergent or divergent. Now, that doesn't give us an actual value. That just tells us if it's convergent or divergent. But if we do want an actual value, we can use this method. For example, the integral from 0 to infinity, sine of x over x. Okay, in this case, we can't use our standard integration techniques. It's not going to be too helpful. However, we can use the Laplace transform to help us out. And we'll see later on that this is going to be pi over 2. So in this case, we can find an exact value for the integral. Okay, so those are the two applications we're going to be looking at. Again, the first one, we'll look at it, but it won't be directly tested. And the second one, We'll have a look at more examples in the Thursday lecture, and this can be tested. Okay, so what is this transformation? So we're going to have some function f of t, some function of time, and we're going to convert it into a new function, capital F of s, given by the following integral. So the Laplace transform of f, we write it like this with the script L, is equal to the integral from 0 to infinity e to the minus st f of t dt. Okay. Now, once we've done all of the integration with respect to t, that all goes away, and we're left with the variable s. So integrating all of the t out, we end up with some function of s, and we write that with a capital F. So if the given function is a lowercase f, then the transform is usually given by a capital F. And then the variable t that's given here, that is converted into the variable s. And usually t, that is for time, and s, that is for frequency. So those are for specific examples. For example, in physics, you're looking at time and frequency, or in circuits, okay, you've got some alternating current in time and it has some frequency. We can use the Laplace transform to study those problems. Okay, in this form as an integral, we get some number of properties. Yeah, and we can prove them. I'll prove a few of these for you, and then the rest I will leave for homework. Okay, so given this integral transformation, there's some properties we can find. So properties, number one, this is the most obvious property, is the fact that this transformation is linear. Okay, which means if we have some function f of t, which is g of t plus alpha h of t, then using this Laplace transform, we end up with capital F of s is equal to g of s plus alpha h of s. Okay, the proof for this is very, very easy. Right, because integration is linear, so the transformation will also be linear. Okay, so f of s, this will be the integral from 0 to infinity e to the minus st, and then our function, that will be g of t plus alpha h of t dt. Now this we can split up into two parts, so we can have the integral from 0 to infinity e to the minus t g of t dt, plus the integral from 0 to infinity e to the minus t alpha h of t dt. Okay, but the alpha is just a constant, we can take that out. So this is going to be the integral from 0 to infinity e to the minus st g of t dt, plus alpha integral from 0 to infinity e to the minus st h of t dt. But now this first integral is just the Laplace transform of g, so we can write that as capital G of s plus alpha. And then the second integral is the Laplace transform of h, so we can write that capital H of s. Yeah, and that ends the proof for this first property. Yeah, very easy. Property number two, it gets a bit more complicated. Let's say we have the function t times f of t. Using the Laplace transform, this gets converted to minus f prime of s. Okay, so little f, that gets converted to capital F, but if we multiply it by t, then that gets converted to minus the derivative of capital F. Okay, let's have a look at the proof for this one. Okay, so we're going to write out the Laplace transform of this. So that's going to be the integral from 0 to infinity e to the minus st t f of t dt. Now notice this t here also appears in this exponential. So we've got a t down here and a t up there. Now, if we just do this little working on the side, d by ds of e to the minus st. So now we're taking the derivative with respect to s. So t is going to be some constant. We can take it down with the derivative. So this will be minus t e to the minus st. Okay, and notice this right-hand side and this underlined side here in pink here, that's the same. So if we take the derivative with respect to s, then we get the t down along with the minus sign, which is what we have here, apart from the minus sign. Okay. So let's put the minus sign on the outside and then take the derivative with respect to s. So minus d by ds, integral from 0 to infinity of e to the minus st. Okay, so the derivative will take down the minus t like we wanted, and then the minus in front will cancel that. And then we have f of t dt. Okay, but now this integral is just the Laplace transform of f. So this is going to be minus d by ds of the Laplace transform. Yeah, but instead of writing it with d by ds, we can write it with prom if we wanted. So that's minus f prime of s. Okay. A little bit of thinking, but not too bad. Okay, let's have a look at property number 3. So here we have f prime of t. So again, the little f that gets sent to capital F. Okay, but if we have the derivative, then this gets mapped using the Laplace transform to s times the Laplace transform minus f at 0. Okay, so how do we manage this? Well, proof. Okay, well, we just want to take the Laplace transform of this. So we're going to have the Laplace transform of the derivative, but just using the definition, that gives us the integral from 0 to infinity, e to the minus st, f prime of t dt. Yeah, that's just the definition of the Laplace transform. Now, what we want is to end up with this capital F. So this derivative on the little f here, we want that to go away. In order to do that, we can use integration by parts. So we can say u equals e to the minus st, and dv is everything else. So f prime of t dt, right? Because dv, if dv is this, then v will be f, which is what we need for the Laplace transform. So du, that will be minus s e to the minus st dt, and v, that will just be f of t. Right, the derivative and the integral, they cancel out, and we just left with the function back. Okay, so the integral from 0 to infinity, e to the minus st, f prime of t dt. This is going to be now the limit as b goes to infinity of u times v, so e to the minus st, f of t, from 0 to b, okay, minus the integral from 0 to infinity, v du, so that will be minus s e to the minus st, f of t dt. Okay, now we can substitute and then take this limit here. So this will be the limit as b goes to infinity, e to the minus sb, f of b, minus e to the 0, that's going to be 1, so just going to be f of 0. Okay, minus and a minus, that makes a plus. The s is a constant, that can come out. Integral 0 to infinity, e to the minus st, f of t dt. Okay, good. Now, what happens when b goes to infinity? Well, here we have e to the minus b. So when b goes to infinity, this exponential is going to go to 0, and all of that will be 0. So we're left with minus f at 0. The limit doesn't affect that, so that's just minus f of 0 plus s. And then this integral on the right here, that's just the Laplace transform of f. So we can write that as capital F of s. Okay, and we're done with that. Now the next one, number 4, is if we have f double prime of t, using the Laplace transform, this gives us s squared f of s minus s f of 0 minus f prime of 0. Okay, very similar to what we did for property number 3, and that will be for homework. Okay, you can give that a go. Very similar to what we did for number 3. Okay, number 5. We have e to the at, where a is some constant, f of t. We use the Laplace transform, and this gives us capital F, the Laplace transform of the little f, at s minus a. So this e to the at acts as a right shifting by a. Right, because we got f of s minus a, so that shifts us to the right by a. Let's have a look at the proof. Yeah, so we want to take the Laplace transform of this. So that's going to be the integral from 0 to infinity of e to the minus st. Okay, that just comes from the transform. Now the function will be e to the at f of t and then dt. Now we've got two exponentials. We can combine them together. So this is going to be the integral from 0 to infinity e to the minus s plus a t f of t dt. Now we want this to look more like the normal transform, right? The minus st. So here in the brackets, let's take out a minus. So this is going to be the integral from 0 to infinity e to the minus s minus a t f of t dt. Okay, so this looks more like the integral transform. But here, instead of s, we have s minus a. So we'll make a little note here that s is now s minus a. Okay, and everything else is the same. We've got the little f. That gets converted to capital F of s. But remember, s now goes to s minus a. So this will be f of s minus a. And that's the end of the proof for that one. Okay, and then the last property number 6. We've got here f of a t. So we've scaled the time variable by some amount a. And then using the Laplace transform, this gets converted to 1 over a, capital F of s over a. Okay, so how do we end up with this? Let's have a look at the proof. So I'll start it and then you can finish it for homework. So we've got the Laplace transform of this. So that's going to be the integral from 0 to infinity e to the minus st f of at et. Okay, now we don't want this at over here. Okay, we want that just to be f of t. So we're going to do a u substitution. So u equals at. So 1 over a du equals dt. So now for homework, see what the bounds change to, change everything to u, and then see if you can get to this right-hand side. So finish for homework. Okay, so those are just some properties that we get from the definition using the integral. Let's have a look at some examples now. Okay, so some examples. Okay, so for the first example, so for this first example here, we're going to have f of t is equal to 1. Okay, nice and easy. And we just want to use the definition of the Laplace transform to find the capital F. Okay, the Laplace transform of f. So capital F of s, this will be the integral from 0 to infinity, e to the minus st, f of t dt. Again, just from the definition. But f of t is just 1, so this will be the integral from 0 to infinity, e to the minus st of 1. Okay, we can write that as the integral from 0 to infinity, e to the minus st dt. Now, to evaluate this, we can write this as a limit. So this will be the limit as b goes to infinity, integral from 0 to b, e to the minus st dt. Okay, so we ignore the limit, do the definite integral, and then take the limit at the end. So that will be the limit as b goes to infinity of this integral as an antiderivative now. So e to the minus st, that will be minus 1 over s, e to the minus st from 0 to b. It will be limit b goes to infinity. If we substitute b, we're going to get minus 1 over s, e to the minus sb, minus and a minus, so that's a plus 1 over s. Okay, if we put in 0, e to the 0, that will just be 1. Now, when b goes to infinity, this whole thing will go to 0, so we're left with 1 over s. So the Laplace transform of 1 becomes 1 over s. Okay, please make a note of this in your books. Okay, we will be seeing this later on. Okay, so just remember, make a note of that. Okay, for the second example, we're going to have f of t equals t. So a bit more complicated than the first one, but not too bad. Okay, so here we want capital F of s. This is going to be equal to the integral from 0 to infinity, e to the minus st, and then we're going to have t as our function there. Okay, now there are two ways to proceed from here. Either we can just use integration by parts to evaluate this directly, or we can go back to our properties and notice here, if we've got t times f of t, then this becomes minus the derivative of the Laplace transform. In this case, we just have t by itself, but if we go back here, that's just the same as calling this f of t 1. Yeah. So we can do that, or we can just do it as an integration by parts problem. Okay, but let's do it as an integration by parts problem. So we're going to have u is equal to t, dv is equal to e to the minus st dt. So du, that will be dt, and v, that will be minus 1 over s, e to the minus st. So f of s, this is going to be the limit as b goes to infinity of uv, so that will be minus 1 over s, the t at the top, e to the minus st from 0 to b. Then we have minus and a minus, so plus 1 over s, integral from 0 to infinity of e to the minus st dt. Okay, now for the limit here, either case, with the limit as b going to infinity, or substituting 0, we end up with 0. And then we get 1 over s, integral from 0 to infinity, e to the minus st dt. Okay, we did this one already, so I'll just put the answer down. That will be 1 over s squared. So we get 1 over s from this prefactor, 1 over s from the integral that we did before. So we get 1 over s squared. And again, just remember making notes of that. Okay, and then the last example for today, number 3, we want to find the transform of sine of t. And then for homework, please follow the working like we did here, but then find for cos of t. So we want to find capital F of s. This is going to be the integral from 0 to infinity, e to the minus st, sine of t dt. Now this we've seen before when we did integration by parts. So remember we had the e to the x sine x dx, we had this integral, and we had the other one, e to the x cos x dx. Okay, we had these two integrals that we looked at a few chapters ago. Okay, so I won't do all of the working again. You can have a look at the notes for that. But here we're going to end up with the limit as b goes to infinity of, and then just doing this like we did before, we're going to end up with minus e to the minus st, s times sine of t plus cos of t, all over s squared plus 1, evaluated from 0 to b. So this antiderivative here, that just follows from what we covered before with those two problems. So this is going to be the limit as b goes to infinity. Let's substitute b. So we're going to have minus e to the minus st, where t is now b. Then s times sine of t, where t is now b, plus cos of b, all over s squared plus 1. Okay, minus and a minus, so plus e to the 0, that's just going to be a 1. Then we're going to have s times sine of 0 plus cos of 0, all over s squared plus 1. Okay, what happens when b goes to infinity? Well, we've got e to the minus b, so when b goes to infinity, this whole thing is going to go to 0. And then for the second term, sine of 0 is 0, cos of 0 is 1, so we end up with 1 over s squared plus 1. And again, please make a note of this in your box. Yeah, so the last thing we're going to be looking at today is the inverse Laplace transform. Inverse Laplace transform. There is a definition for the inverse Laplace transform. However, it is far too complicated for us to look at right now. So instead of looking at the general inverse, what we're going to do instead is make a table of the transformations. So from f of t to f of s. So using the Laplace transform, we can go that way. And then from the table, given the transformed function, we can just look at the table and go backwards using the inverse Laplace transform. Okay, so this inverse we won't calculate. We'll just have a look at the table to see which direction we're going in. So for example, if f of t is 1, we had a look at this earlier here. That was 1 over s. So in the table, we can put here 1 over s. So going from left to right, that's the Laplace transform. Now, if I give you 1 over s, then the inverse Laplace transform is now going right to left, and it's just going to be 1. And then the second one, t, we found was 1 over s squared. So again, going left to right, t gets transformed to 1 over s squared, 1 over s squared gets inverse transformed back to t. Okay. Then we had the example with sine of t. That gets transformed to 1 over s squared plus 1. And 1 over s squared plus 1 gets inverse transformed back to sine of t. And then for homework, you're going to fill in the space for cos of t. Okay, so on Thursday, we're going to have a look at a few more problems to add to our table here. And then we're also going to be looking at solving improper integrals using the Laplace transform. Okay, so Thursday plan. So a few more examples. Okay, and then solving improper integrals. Okay, and then the method of solving differential equations using the Laplace transform. We'll have a look at that briefly on the Thursday, but we'll look at that in a much more detailed way when we look at differential equations later in the year. So that's going to be it for today. If you have any questions, please email me or the tutors. The solutions for the improper integral tutorial is already up, so you can have a look at that. And I have also posted some extra questions on mixed integration, improper integrals, and a few more integral proofs. Yeah, like we had in the class test one. Okay, but if you have any questions, just let me know and then I can assist you.